This tutorial is titled Analytics over the Hows and the Whys, and this is jointly prepared across three of us, me, Dinesh Garg from IBM Research, and Shirish from Indian Institute of Science. And I should mention here that this is being recorded after the conference, ICWSM conference, so this is for the benefit of the wider audience. So going forward, we'll just start with an overview of this tutorial. The first thing that I would like to cover in this would be the CQA setting, the community question answering setting, which is the focus of this tutorial. And we'll look at differences of the CQA setting from traditional information retrieval as well as from Factoid question answering systems. We'll look at CQA systems, their operation, and the data they produce, which will be the raw material for the analytics that we build upon them. And we'll look quickly at knowledge reuse mechanisms from artificial intelligence. So that will be mostly about case-based reasoning, which has a similar structure to the work from CQA systems. And also we'll look at textual case-based reasoning, which is a text version of traditional case-based reasoning. We'll look at some CQA tasks. We'll focus on the lexical chasm in CQA datasets, which is an important challenge that has been addressed across numerous papers. Then we'll look at CQA retrieval, which will be a deep dive into a few methods for CQA retrieval. We'll group the techniques into different schools of techniques, and we'll look at some of them in detail. Then we'll look at other CQA tasks such as QA procurement, quality and hardness prediction. We'll look at clustering, expertise modeling, and query suggestions as well. And following that, we'll look at CQA analytics as a specialization of multi-view data processing. And we'll look at some methods from general multi-view data processing. I also hope to cover some amount of detail, some data sets that are appropriate for CQA tasks. And this will be followed by broad research directions, which are promising at this point when I'm recording this talk. Okay, and that will bring us to the end of the tutorial. Okay, so moving on, let's look at the CQA setting, community question answering systems, the data they produce, and the analytical tasks that we address. So let's look at finding information on the web and how people do that in the present day, right? So you have a user who has a particular kind of information need, let's say, and that information need is typically phrased in the form of a search query that is submitted to a web search engine. And the web search engine processes this query and comes back with a set of results, which are typically a set of ordered, an ordered set of web pages of pages from the web. Okay. And so most web search engines work best for short information retrieval type of queries involving 2 to 4 words. So let's look at what people ask in web search engines. So this is a broad set of questions that I found from some survey which summarizes the research in web search and so on. So these are some typical kind of questions. So how much should I weigh? What does my name mean? And things like even as open-ended as what is true love and what is and very specific things as well as like a particular address and so on. So these kinds of queries form 10 to 20% of all queries. Other queries, the typical form of web search query is just 2 to 4 words, and these are longer queries. And among the longer queries, these are some typical longer queries. And these longer queries form around 10 to 20% of all queries that are submitted to web search engines. So going forward, let's look at Factoid question answering systems and what they do. So a Factoid question answering kind of query has many words, and the response is typically a concept or a noun phrase. So it's much smaller. It's much smaller as compared to the question part of it, and there is only one correct response to a query. And there are numerous Factoid question answering systems in the web. There is one called START, which comes from the MIT AI lab. So where I've shown the screenshot where somebody is querying the START question answering system with the query, the first president of the United States, and the answer to that would be George Washington. So there is a single correct answer, and the correct answer is a smallish text segment, which could be a noun phrase. In this case, it's just 2 words corresponding to the name of the first president of the United States. Okay, so moving forward, let's look at an example approach that is adopted within factoid question answering systems. So you have a question, and you would typically rewrite the query. You have a question like where is the museum, where is a particular museum located? You might need to rewrite the query into different kinds of versions of the query. You would submit these to search engines. You would collect the results from the search engines for those queries, and you would collect the summaries and mine engrams. Engrams are like word engrams, so you could look at sequences of words that are frequent among the results in the web search. And the results corresponding to the web search queries that you have formulated. Then you would filter these engrams and tile these engrams, like place them together so that they align well, and so on and so forth, and you might get the end best answers. And this is a particular instance of a factoid question answering system, which is the Ask MSR system. Okay, this need not be the case with this architecture is just specific to that system, but it gives you a flavor of the techniques that are used in factoid question answering systems. So the raw material for factoid question answering systems are text, and they are not question answer archives, as we'll see in the case of CQA systems. Okay, so let's look at this set of queries that I presented in the previous slide, and let's ask maybe as to which among these are factoid question answering queries, right? So how much should I weigh is a very subjective query. There is no one correct answer, which is a small noun-phrase or anything. You might need a descriptive answer for some of these queries. You might have multiple answers for some of the queries, and there might not be any answer for some of these queries as well. For example, what is the meaning of life? There is no one particular answer. And there could be long answers for some of these queries, and there could be some of them in this list are of the factoid QA type, which is basically one correct answer. So I've outlined or highlighted one of those queries, which is who is the richest man in the world. There is one answer, and the answer is a small text segment, which should be the name of the person. Okay, so moving ahead, let's look at the core focus of our tutorial, which is community question answering systems, right? So the community question answering systems deal with a different kind of query, which is typically a how or a why question, or one that needs a descriptive answer. And the answer is typically longer than that for factoid question answering systems, and potentially has many descriptive sentences. There is typically no one correct response, and answers could be graded on different levels of quality. Okay, so let's look at an example from a human in the loop CQA service. So you might ask a question: is international travel without passports possible? Right? And surprisingly, it seems that there are a lot of scenarios where somebody can travel internationally, cross international boundaries without having a passport, which is especially true in the EU area, where they have the Schengen Treaty and so on. But there are other interesting cases as well. For example, this answer segment that I've highlighted says that there are a few countries that allow their citizens to fly into their own country with just an expired passport or other proof of citizenship, right? And this happens to be the case even for Canadians in some parts when you want to fly out of a different country and go back to your home, and so on and so forth. So this, there are numerous instances of cases where international travel without passports is possible, and people could talk about different scenarios and different answers, and these are all valid answers, good quality answers to the query. Okay, so let's look at the holy grail of computational CQA, which is what we aspire to achieve, which we may never achieve, but it's good to have a goal to work towards. Right, so you have a person, you have a user who has a particular information need, and that information need is formulated in the form of a how or why query. Okay, and that is given to a CQA engine, and the CQA engine comes back with a descriptive answer that exactly addresses the how or why query that the user wants. Right, the user wants information too. So a CQA engine that can assimilate the query, look up pertinent information from the web or elsewhere, and return a descriptive answer that answers the query for the user. So this is what we would like to have. Okay, and let's look at the current state of computational CQA, and let's look at how far we have reached and how far we need to go to achieve what could be formulated as a holy grail, like we saw in the last slide. So the user has a how or why query, right? And that is given to a CQA engine, which works upon archives from human-in-the-loop CQA systems. So these archives contain questions and answers, both posted by humans. And the CQA engine works upon these archives from human-in-the-loop CQA systems and provides a user with a list of CQA pairs from the archive. And these lists of CQA pairs are typically ordered and presented in the form of ranked lists, much like any web search engine would do. And that's what is typically done by a present-day CQA engine. And the critical resource for the CQA engine is basically archives from human-in-the-loop CQA systems, and that forms our data, our data raw material, which we'll look at in some amount of detail in the next few slides. Let's look at the types of data that we can get from CQA systems. The question, of course, and the user posting the question, which is typically represented by means of a user ID, and there is a time at which the question was posted, right? And categories associated with the question. In many cases, there would be categories that are automatically inferred, or in certain cases, you might actually do a human selection. The questioner might associate a category, or there could be a combination of that. For example, the system might suggest some categories, and the user might take those categories or may reject them. And there are also answers and users posting the answer, the time that the user posted the answer, the number of upvotes and or downvotes, and the IDs of the people who upvoted or downvoted. So the IDs are kind of important because you can infer a social network underneath these question answer pairs. And in certain cases, there would be an admin chosen best answer or a collapsed answer because it has been heavily downvoted, as in the case of Quora, as we'll see quite soon. And there could be comments posted by the user on the questions and or comments posted by users on the answers. And with each user ID, you might have a reputation of the user gathered through historical contributions as well. So this forms the typical kind of raw material that you would get from a CQA system. So let's look at Yahoo Answers and the operation of a typical Yahoo Answers. Yahoo Answers question answer session, or not to say a session, but a thread maybe. A user comes in and posts a question, and another user comes in at some point in time afterward and comes and posts an answer. And there is a third user who comes and posts another answer. And there could be a fourth user who comes in and says that thinks that one of the answers is very good and upvotes a previous answer. And there could be another user who comes in and downvotes a previous answer, right? And at the end of 4 days, the questioner can choose a best answer among the answers that his or her question has gathered over the last 4 days. So users the guidelines for the users is that users may use Wikipedia or any other source of information to answer a question. Comments may be posted anytime, even after the 4-day limit. And the user contributing the answer, which is chosen as the best, is credited with 10 loyalty points. So that does not convert to cash, but it's some kind incentivizes people to enter good answers. Okay, so let's look at Quora, which has a similar structure with some additional features and some constraints. And Quora also allows for anonymous question asking and anonymous answering. And some heavily downvoted answers in Quora are sometimes collapsed and not even shown in the default view for other users. And so the data from CQA systems, in some sense, to summarize, you have a question and you have answers associated with it. So there are multiple answers associated with the question because multiple users may come in and answer the same question. And you have metadata associated with the question. You have metadata associated with each of the answers, right? And you have a lot of these threads. You can call these threads. A question starts a thread, and there are multiple answers. So a question followed by multiple answers and a set of answers forms a thread. And you have a bunch of these threads, and that forms the raw material or the data from the CQA systems that would be used by CQA analytics systems to do various tasks. Okay, so there are other sources of CQA-like data. So CQA data, as we saw, would be a typical how or why question, typically a how or why question followed by a bunch of answers. And these kinds of how or why questions and answers could be procured from other kinds of data sources as well. So there could be forums where people ask questions and people answer. There could be things like domain-specific forums like Flyer Talk, where people ask queries about flights and traveling on flights and so on and so forth, maybe transiting through airports and so on. There could be TripAdvisor, which is mostly a tourism-focused forum. And there could be reports from other kinds of services. Like, for example, the health service produces maybe text reports of what are the symptoms that a user presented with and the diagnosis that was made against a user, against a patient. And maybe the police service also prepares reports about what about an incident and what was done about that incident, and so on and so forth. Okay, so moving on. Forums contain user contributed question answers, whereas medical and crime reports talk about issues encountered and the solution to it. So you can think of them as problem solution, because the symptom is a problem that is presented to a medical person, and who comes up with a solution, which is basically the diagnosis associated with the symptom. Okay. So let's look quickly at knowledge reuse mechanisms from AI, and this is fairly important because this is a field from AI which is pretty old, many decades old, and that has been looking at a problem with a similar structure, with tasks which have a similar structure as to what we would look at in CQA systems. So the field itself is called case-based reasoning. So case-based reasoning is a process of solving new problems based on the solutions of similar past problems. And I would reckon that you would recognize the parallel that we have between CBR and CQA analytics. One of the core assumptions behind CBR is that similar problems have similar solutions. Okay, now, and the raw material in CBR systems are a repository of problem solution pairs called cases, and the repository itself is called the case base. So they have their own terminologies. So you should notice the similarity between this setting and that of CQA data. And I would like to point out here that similar problems have similar solutions is an assumption that is likely to be valid in the case of how and why questions as well. Right. So in CBR it's called problem solution pairs. We have question answer pairs. So it's practically of a similar structure in some sense, if you want to think of it that way. So let's look at the CBR idea as such, right? So there is a problem space, a space of problems in which there are instances of different problems, and each of these problems might be associated with a solution each from the solution space. And if you have a problem having multiple solutions, maybe you can duplicate the problem and create multiple pairs, just to conform to this format. So there is a problem space, there is a solution space, and there are correspondences between them by way of links between problems and solutions. And when a new problem comes in, you find similar problems to it, and you find their solutions, and you use those solutions in order to derive at a solution to that problem. Okay, so that's what we do in the case of CBR. So let's look at some examples of real-world CBR. An auto mechanic who fixes an engine by recollecting another car that exhibited similar symptoms and what she had done in order to address the problem in those cars. So that is a typical example of a CBR system in operation, although it's human performing the operation as against machines. And a lawyer who advocates a particular outcome in a trial based on legal precedents, or a judge who creates case law. All of these are doing CBR in some sense. A doctor who is looking at a patient makes use of historical symptom diagnosis pairs to make a diagnosis for the patient. So case-based reasoning is a prominent kind of analogy making, and that is pervasive in the real world. It's just that you're lifting that kind of a structure and using it within computational systems. So that's what case-based reasoning tries to do. So let's look at the CBR process as such, right? So you start with what is called a case base, which has problem solution documents. So these are two-part, not documents. These are two-part, entities. There is a problem and there is an associated solution, and the collection of these things forms a case base. And there is a new case which contains only the problem part, which comes in, and you retrieve similar cases to that new case. Okay. So similar cases are problem solution pair. So you retrieve similar cases, and then you try to reuse those cases using something called reuse rules, which we'll see some examples of in the next few slides. And the reuse rules gives you a suggested solution for this new case, which might need to be revised in order to with human in the loop processes in order to arrive at a solution that is appropriate for that new case, and that's what is called a conformed solution. That would be retained in the case base, so that can also be leveraged in case of new problems coming in later on, right? Okay, so the CBR process. Let's look at some observations from the CBR process. So you would notice that it is lazy learning. So there is no statistical model learned over the case base. So it's just about remembering the cases. And you should contrast this with learning for machine learning within the machine learning world, where the solution is one among a finite set of classes, and you learn a complex statistical model that maps from data objects to a set of classes. So so the CBR itself is applicable best for domains where the reuse rules can be defined well. Let's look at one such domain, which could be the transportation domain, where the problem could be a source and destination pair, and essentially the query is about how can I get from the source to the destination, and the solution is a trip, which is basically an itinerary to get from the source to the destination. So the trip from A to B and from B to C can be concatenated to form a trip from A to C. So if you only have trips from A to B and B to C in the repository, queries and their associated answers, you can kind of answer a question, answer a problem that comes from the user regarding itineraries for A to C, right? And let's look at the CBR process for textual case bases, for case bases where the problem and the solution are in the form of text, right? So if you look at that, you're trying to basically define reuse rules, which take a set of question answer pairs and come up with an answer for a new question, which is also expressed in text, right? So you're taking a bunch of text segments or text documents and trying to do something with it to come up with a solution for a new problem. So in some sense, you can think of that as kind of bordering on natural language generation, natural language understanding, or kind of intersection of these two fields and so on. So textual CBR is a subfield of CBR trying to address CBR questions for textual case bases. Okay, so some popular challenges that have been addressed within the textual CBR domain is how to convert textual case bases to structured representations so that the reuse rules can be defined easily. So how can I convert the unstructured text document into a structured representation such that the reuse rules can be defined within that representation, like we did for the transportation domain, if you think of it that way, right? So how to automatically generate representations for textual CBR is what people have been occupied with within the textual CBR domain. So this line of research kind of takes the problem further away from the NLP domain. You're converting text to structured data, and you probably would do that in a very domain-specific manner, and that would kind of take the effort from the NLP domain and towards the CBR domain. And there has been a parallel effort in the NLP or knowledge management world, which addresses the task of being able to use historical question answer pairs or historical problem solutions in order to address a new problem. And that puts the retrieval problem in the center stage. So you have the case base and you have a new case, and you retrieve a similar or a reusable cases for the new case from the case base. So this kind of puts the retrieval problem in the center stage. So this retrieval problem makes the tasks similar to what we would traditionally address within the information retrieval and the NLP communities. Okay, so let's look at some tasks in CQA analytics, and beyond which we'll look at some concrete methods for addressing those tasks. So we'll build an overview of the task landscape so as to guide the remainder of the tutorial. So you have a QA archive. You should notice that I've replaced the phrase case base with QA archive, right? And you might want to create this QA archive in the first place, right? So you might have things like Yahoo Answers, Quora, and the now defunct Google Answers, which have data in the form of a question answer format, which you can take and readily create QA archives out of it. So in some sense, if you want to have, if you have multiple answers to a question, as is typical in the case of Yahoo Answers and Quora, you might want to duplicate the question so that you create these QA pairs that can go into the QA archive. Or you might want to harvest this kind of QA data from forums and reports, right? Like we saw in the case of health services and the police service and so on. In which case you might want to do a more fancy processing of the data from those repositories, of data from the forums, in order to arrive at QA archives. So you're trying to convert forum data into QA pairs. So you might want to throw away things that are not related to questions and answers, such as comments, clarifications, and so on, or maybe merge them into questions and answers as may be necessary. And once you've created the QA archive, you might need to organize them in some manner, right? For example, you might need to say that the first and the fourth QA pairs are related to the same topic, so they are part of the same color. Here I've colored them as black, and the second and the third QA are kind of part of the same topic, so they're colored with the same color as well. So you might want to bring some organization within the QA archive, such as clustering, topic modeling, etc. And you might want to eliminate some of these QA pairs from the QA archive, because you might have accumulated a lot of junk, or you might have accumulated some QA pairs which are no longer useful because you've gotten much better answers to those to those questions later on in time. So you might want to get rid of some of the QA archives, and that would form the maintenance part of the system. And you might have a user base sitting behind the QA archive, which is basically the network of questioners, network of answerers, and so on and so forth. And this user base might have links between them if there is an underlying social network, as is the case with Quora and Yahoo Answers and so on. People can follow other users on Quora and Yahoo Answers. And I'm not sure about the operation of Google Answers, but I would assume that there would be a similar thing here. You might want to do expertise modeling within the user base. And you might want to do expert identification. Who would be the expert for this kind of a topic, and so on. So Quora does that to some extent, although maybe not as automatically, maybe with human in the loop kind of process. And let's look at the runtime operation, which is kind of the most interesting part of the system. The runtime operation would make use of the QA archive as well as the user base and handle a new question. So you have a new question, and that is taken by the runtime engine. Which makes use of the QA archive as the primary resource as well as the user base. And you might want to look at the hardness of the question. You might want to estimate what is the hardness of the question. You might want to estimate the quality of the question, whether it's a good quality question or a bad quality question. If it's a bad quality question, you might want to ask the user whether she might want to rephrase the question. And you might want to retrieve similar questions, retrieve usable answers, retrieve similar question answer pairs, and so on. And retrieve potential answers, which is a retrieval in the user base space. And this has been a popular research field, the runtime operation, which is basically about taking a new question, making use of the QA archive and potentially the user base as well, and doing various things predominantly in the retrieval space, but also things like hardness, quality prediction, and so on. Okay, so we'll go further and look at some of the challenges in CQA retrieval, and in particular, we'll look at the lexical chasm in CQA retrieval, which kind of differentiates CQA analytics from most of information retrieval. So let's start with information retrieval, which is a conventional retrieval system, which takes in which uses a document archive, which can process a query, which is formulated in the form of 2 or 3 short words. Or a document could also be given as a query, and you would get a set of 11 documents. So here, in the CQA retrieval space, you have a QA archive, and you get a new question, and you want to come up with 11 QA pairs. And you might kind of compare and contrast these kinds of two streams of tasks. And one thing to notice is that the QA archive contains 2 types of information. One is question part and the other is answer part. And the query is only one of those types. The simple way to model it within the conventional retrieval scenario would be to just throw away all the answer parts of the QA archive, right? And then do a retrieval just with the question part, which would make it closer to the information retrieval, conventional retrieval kind of scenario. But then you are losing valuable information that is contained in the answer part. So typically, you would make use of the question and the answer part both in the QA archive in order to get to 11 QA pairs. So that is kind of the lexical chasm, which is one of the major challenges that people address in CQA retrieval. So one of the things that makes the lexical chasm an interesting challenge is that answers need not be more similar to the question than non-answers. So here, some people, this was from a paper in 2011, if I recollect correctly. So they were trying to look at whether you can have an assumption that an answer is more similar to the question than non-answers, right? and they found that answers are not more similar to the question than non-answers. And this is a plot in terms of the similarity histogram that they created. So you take an answer and you compute the cosine similar, and you get all its answers. So you take a question, look at all its answers, and come up with the cosine similarity distribution of all those answers, right? And build a histogram kind of plot. And you do the same thing with non-answers, and you get similar plots. So essentially, what they're trying to say is that just making the assumption that answers might be lexically more similar to questions does not lead you to a good quality retrieval model. In a sense, it might retrieval as many non-answers as answers. So we're talking about similarity as assessed by a measure of the number of common words. So that's what they used, and this was 2011, during which time TF-IDF cosine was still a popular text similarity measure. Okay, so let's look at an illustration of the lexical chasm problem, right? And while the lexical similarity in terms of the number of common words doesn't tell us anything, there are interesting correlations that could be used in order to build CQA retrieval systems. So that's what we'll look at in terms of what we can leverage, right? So let's look at an IT support question answer data set where the question unigrams could be things like disk, network. Question unigrams as in question words. Popular question words could be disk, network, cable, router, etc. And popular answer words could be format, reboot, restart, and plug. And as you might expect, there are interesting correlations between these words. So the appearance of disk in the question might enhance the chance that a format would be part of the answer associated with that question. And similar is the case with cable and plug, and similar is the case with router and restart, for example. So the intuitive next step is about so we found that maybe looking at the number of common words between questions and answers doesn't say anything. What about modeling QA word correlations? What about modeling word correlations between the question and the answer parts, and making use of that in order to arrive at a better retrieval system? So the word correlations across different vocabularies has been an age-old problem. So discovering and modeling correlations using parallel data goes back a long way, and in the non-computational world, it goes back even to the 18th century, where people discovered from archaeological efforts in Egypt, I suppose, something called Rosetta Stone, which had the same inscription or the same decree by an emperor in 3 different languages. One is Greek, one is Demotic, and the other one is hieroglyphic. So it's the same kind of decree, because they got it from an archaeological context where you expect it to be an emperor who wants to popularize some of his commands to the public, and so he or she might have created this kind of a stone with different languages that are popular within the country that he or she is ruling, right? So it took 20 to 30 years to decode. So by decoding, I mean you're trying to find the word correlations between Greek and Demotic, and trying to and also in this case, I think one of them, which is Demotic, was a very less understood language. So they were trying to understand what are the words in those language, what are the words in that language, and what are the meanings of some of the words in that language. So it took around 20 to 30 years to decode this one. But parallel data in the present age is much more abundant, and it comes from a variety of contexts. So one is the Canadian parliamentary debates available in both French and English, and this kind of was leveraged in one of the earliest statistical machine translation models in the early 90s, I suppose. So the parliamentary debates are published in both French and English. So there are documents which mean the same thing, but one written in French, one written in English, right? And the UN documents also form a rich set of parallel text. So it's available in Arabic, Chinese, English, French, Russian, and Spanish. Okay. And so you have parallel text in the present age from various sources, and 2 of these sources are the Canadian Parliament and the UN documents. So with that, we will go to CQA retrieval in the next part of the video, where we will look at techniques for CQA retrieval, and we'll see how to, what are the building blocks that people have used in order to build CQA retrieval techniques and so on. But this part of the video ends here.